Hey everyone, and welcome to my little lab video for the thermodynamics lab. So this lab you aren't going to be actually doing, physically manipulating stuff. You're going to be watching chemical reactions performed in YouTube videos. And just in case they're not clear, I wanted to do this sort of walkthrough. So normally in class I would perform these or I would watch the videos with you. And so just in case it's not clear doing it by yourself, I wanted to make this sort of walkthrough video. So the first reaction you're going to watch is the spontaneous reaction of solid sodium in water. And it's pretty explosive. So this teacher adds sodium to water. This is just water. And notice all this gas coming off. This is hydrogen gas, which is super flammable, which is why it lights on fire. It lights on fire because this is a very exothermic reaction, and the energy from the reaction is enough to ignite that hydrogen gas. And so you get a nice burn. Sometimes it sparks and does a little firework thingy. Firework pops there. What's happening to the water is the sodium is actually sort of dissolving in the water, but it's forming sodium hydroxide. So it's having a very violent reaction with water and forming sodium hydroxide, which is a base. So another common iteration on this reaction is to add a pH indicator to the water, and you can see it change colors as it becomes more basic. But it is fun to watch the sodium catch on fire. When I have done this in lab before, sometimes the little popping at the end is so explosive, it actually explodes the beaker. So you always have to do this in a chemical hood. Be very careful because this is a strong base, sodium hydroxide. So when if it explodes and goes everywhere, I've watched other demos on YouTube where teachers will do it just on a desktop, and a lot of times at the end when the sodium crackles, that a little bit of the sodium will actually go flying out, and it could hit somebody in the room and cause a chemical burn. So I'm always super careful and do it in the hood in case there's any explosiveness to it, which is not uncommon. So feel free to Google around and watch other YouTube videos of sodium and water. There's also videos of people throwing like giant sodium chunks into like a lake. Okay, which I don't encourage you to do. So that's the first one. So then the questions are, it asks you to just, briefly describe what happens, what were your observations, is the reaction endothermic or exothermic, and then a thermodynamic question here for you. I gave you a table of, oh, this is the wrong reaction. Oh, sorry. Here's the sodium one. So you're going to describe what happens. I want you to write the balanced equation for sodium reacting in water to form hydrogen gas and aqueous sodium hydroxide. You should know how to write the formulas for all of these things and then balance the equation. It's a little bit exercising your brain from last semester. Just based on what you saw in the video, do you think the reaction is endothermic or exothermic? Did it absorb energy or did it create energy? And then also based on your observations, do you think whether it's in the video or in the equation that you wrote out in part B, do you think the reaction involves an increase or a decrease in entropy? And I want you to think about what you know about factors that increase or decrease entropy. So this one's really purely observational, this problem. The second reaction, we're going to watch the spontaneous reaction between barium hydroxide and ammonium chloride. I like this professor or teacher. He's got a fun British accent, but you can watch that later. You can watch it separately. So he's got some barium hydroxide, and he also has some ammonium chloride, and he's going to mix the two together. I'm going to do this on faster speed. I do that. All right, so we're going to watch it on fast forward. All right, so he's going to mix them together, but first he's just going to wet this block here, this block of wood with a little bit of water, and we'll see why. So he's crunching that up because it's a little bit clumpy, and now he's going to mix them together and use the stir bar to stir it. And you can see it kind of changed consistency. It looks a little bit wet, and that's because one of the salts is a hydrate, so it does actually have water. And so water is actually forming in this reaction between these two substances. And this reaction is absorbing heat. It's an endothermic reaction. It's absorbing heat from the environment, and it's going to be absorbing it from the water that it's sitting on top of. And what happens when you absorb heat out of water? The water gets cold and the water freezes. And so the water ends up freezing to the glass and the block of ice and sticking them together. So now the beaker is stuck to the block of ice because it has, or it's stuck to the block of wood because it has frozen. And one of the students asks him, well, how cold is it getting? And he sticks a thermometer in there and he says, well, it's already at -5, but it's going down. And the thermometer only goes to -10, but it will actually get even colder than -10. And so that's a classic example of an endothermic reaction that absorbs heat from the surroundings. And when that heat's coming from water, it actually freezes the water. And it feels cold if you touched it. I think he said that you could even feel like condensation on or like ice, frost forming on the outside of the beakers. So then I have some questions about that one for you to answer. Again, I want you to write your observations down, briefly describe what happened. And then this is sort of a little bit more of an application problem. So this is thermodynamic information that I looked up for all of the substances in this equation, and here's the equation. I don't make you write it out. I provide you the balanced equation for this reaction, but I want you to use this information and I want you to calculate what is the enthalpy of the reaction, calculate what is the entropy change of the reaction, and then use those two values to calculate the Gibbs free energy using what we've learned in class in chapter 12. And this one's a fun one. This is the sugar snake reaction. So you can do this at home, but I'm not encouraging it, or I don't want to be liable. It's very flammable. So, but basically all you do is you add like lighter fluid to some sand. That's going to be your fuel, or you can get like a fuel cup, like for what do you call it? Like a little gas stove thing. Then you mix sugar and baking soda together and you put them on top of the fuel and you light the fuel. And you'll see at first everything gets kind of black. The sugar gets kind of black, but then it starts to grow. This black stuff, kind of blackish gray stuff, starts to grow out. So the black is from carbon, and the grayish whitish stuff is like sodium carbonate. And they mix, those are two solids that are formed in this chemical reaction. But what's also formed in this reaction is water vapor and carbon dioxide. And those kind of push those solid products out. And it forms this weird looking black snake. And it looks kind of magical, but it's just these solid products getting pushed out by the production of water vapor and carbon dioxide gas. And so again, I ask you some thermodynamic questions. First, tell me what your observations are. Here we go. And I also give you the different reactions that are happening. So this is, there's an overall reaction. We could add all three of these reactions together to get the overall reaction, but I broke it down into sort of the three separate things that are happening here. So the first is that sodium bicarbonate, which is baking soda, all right, is breaking down into sodium carbonate and carbon dioxide and water vapor. But also the sucrose, which is the sugar, is combusting. It's burning in oxygen to form carbon dioxide and water. And some of the sucrose is not going through combustion, but it's actually decomposing into carbon, which is black, and gives that char color, and water. And so overall, what's being made, the products are sodium carbonate, which is that like a whitish powder, carbon, which is a black solid, and then lots of water vapor and carbon dioxide. So you'll describe what happens, and then for each of these three reactions and the information I've given you, I want you to indicate whether it's endothermic or exothermic, indicate whether each reaction has an increase or a decrease in entropy, and then indicate which of those reactions is always having a delta G of less than 0, or a negative delta G. And then the last part is I want you to calculate the temperature at which sodium bicarbonate decomposition will be spontaneous, this one right here. All right, this is actually an example of reactions that are coupled in order to make a non-spontaneous reaction happen spontaneously. And then the last one is the spontaneous reaction of copper and silver nitrate. So in this reaction, we take a solution of silver nitrate, it's an aqueous solution, and we stick a copper wire in it. And am I watching this at a fast speed? No, I'm going to speed it up though. All right, but you can already start seeing the silver is starting to precipitate onto the copper wire here. All right, and the silver forms these kind of cool needles. So I don't know, I don't know if this is a time lapse or a real-time video. I assume that it's time lapsed. So it does take time for this to happen, probably at least a couple of hours. But you see the formation of these little needle-like pieces of silver forming. It's really pretty. But you'll also notice that the solution is starting to turn kind of bluish green. And that's because copper ions move into solution. And the copper ions have a bluish greenish color. And so we're still watching this reaction go. The needles are actually getting a little bit bigger. So this is solid silver precipitating out of solution. The silver ions were floating around in aqueous solution, but they are precipitating and forming a solid on the copper wire there. It looks pretty cool. So then there's some questions about that. Briefly describe what you saw happen. Write the balanced equation. It's a single displacement reaction. If you don't remember what a single displacement reaction is, look it up back in chapter, I don't remember what chapter, earlier chapter in the textbook. Between solid copper and aqueous silver nitrate to form solid silver and aqueous copper 2 nitrate. So again, you should be able to just write that from the sentence form. You don't even have to look up a single displacement reaction. Hopefully writing it out will remind you what it is. And then based on your observations, I want to know, does this reaction involve an increase or a decrease in entropy? What do you think? Explain. I want you to, and whenever I say explain, I don't want you to just answer the question increase or decrease. So I want you to give me your explanation. Why do you think that? What observation made you think that? And then here's a sort of thermodynamic problem around this reaction. So while this reaction is spontaneous at room temperature, which is what we just witnessed, it's not spontaneous at all temperatures. So in this question, I want you to calculate the temperature at which the reaction becomes spontaneous. So in other words, you should set G, delta G, that gives free energy, to 0 and solve for temperature. And I give you the enthalpy and the entropy for this reaction. And then I want you to tell me, is the reaction going to be spontaneous at temperatures higher than that or lower than that? In other words, is this going to be a reaction that's spontaneous at high temperatures or low temperatures? We already know it's not a reaction that's spontaneous at all temperatures. All right, and that is our thermodynamics lab. I hope you enjoy.